Great. Okay. Sorry. Can you hear me? Is it okay? Okay. Excellent. Well, thanks very much for the kind invitation to talk. It's always fantastic to be here in Santa Barbara. I'm going to talk about my perspective on random quantum circuits. So random quantum circuits from a complexity theoretic perspective. Now, this talk is going to be based on two joint works with my collaborators. The first work is back in 2019, joint work with Adam Boland, Chinmay Nurki, and Umesh Vazirani. And then the more recent paper from just a little bit less than a year ago is joint work with Adam Boland, Zef Landau, and Yunchao Liu. Okay, so the starting point for this talk, and I think we all know this, we've already heard about this in the talks and so on, is that we're now in this really exciting era in which we've seen the first claims of quantum advantage. That have been experimentally implemented. First, of course, by Google in late 2019, who implemented the so-called random circuit sampling proposal on 53 superconducting qubits. And more recently, the Gaussian boson sampling proposal for quantum advantage in a linear optical architecture that was implemented originally by USTC in late 2020, and more recently by Xanadu only a few months back. Okay. And I guess this talk is about the latest complexity theoretic reason or evidence to believe that these random quantum circuit experiments, and both of these are actually sort of different special cases of random circuits, might be solving classically intractable problems. Okay, sort of formalizing why we think that quantum supremacy, may or may not have happened with these experiments. Okay, but sounds simple enough, but let's take a step back, actually. There's actually some subtle questions that we need to address right off the bat. So first of all, what do we mean when we say classically intractable? Well, here I see sort of a fork in the road, and we're going to take it. There's this sort of two settings. The setting we have in mind when I talk about classically intractable is the sort of classical setting or rather the traditional setting of complexity theory, which is asymptotic hardness. So in other words, the goal of today's talk is to give you proofs, sort of rigorous proofs, that there's no classical simulation algorithm that simulates the random quantum circuit with a running time that scales polynomially in the system size and the number of qubits. Okay? And we're complexity theorists, we're going to hold ourselves to a really high standard. And it's really hard to do this. The goal is not merely to show that the best known algorithm, like some tensor network simulation algorithm that currently exists, doesn't work. The goal is rather to show that, there will never be a classical algorithm that will exist to simulate these quantum circuits, no matter how complicated that algorithm is. Right? So it's really very, very stringent. On the other hand, I think that, this is sort of necessary, proving asymptotic hardness, but it's not sufficient. It's not sufficient to show quantum advantage, fundamentally because we also need to consider non-asymptotic, issues. If you think about it, if we only were in asymptopia, right, then there would really be not very much reason that the number 53 in Google's experiment would be so important. It's really not much more important than 30 or 20 or 2 for that matter. The point is, for us in asymptopia, we're really considering the scaling behavior. That there shouldn't be an algorithm that runs with polynomial running time in the system size. And so it's also, I think, in tandem important to consider these non-asymptotic issues. Things like the best supercomputer that currently exists running the best method that currently exists takes a long amount of human time as compared with running time to solve the problem at the same system size as the experiment. So it's super important. My group has actually been thinking about this recently, although it's not been our focus, especially in the context of simulating noisy systems with tensor network approaches. But today's talk is going to be in this asymptotic picture. Okay? Cool. By the way, you should stop and ask questions if you have some. Okay, but what do we mean by classical simulation algorithm? Right? So again, I said our goal in the asymptotic picture was to prove that there's no efficient classical simulation algorithm, but what does it even mean? So here's what I have in mind. The goal is to prove the impossibility of what I'm going to call an efficient classical sampler. And what that does, that's a classical algorithm that simulates an idealized version of the quantum experiment. Okay, of the noiseless quantum experiment. So that is, the classical algorithm should take as input a description of a random quantum circuit which implicitly specifies a measurement outcome distribution. I'll call that D sub C. That's the distribution if I started in the all zero initial state, ran my circuit on n qubits, and then measured all n qubits, you would get D sub C, again with no noise. And then the goal of the classical algorithm, given this classical description of the random quantum circuit, is it should do the same thing that the quantum algorithm does, namely outputs a sample from any distribution X that's close to the distribution D sub C. Okay? The metric we're using for closeness here is total variation distance. It's not super important from the perspective of my talk. Many metrics would work, but I think the only thing I want to say at this point is just to clear up some confusion that's sort of existed in the literature for a long time. The reason we're interested in this total variation distance metric has actually nothing to do with physical noise. It's not a good measure for physical noise. Rather, what it's trying to model is the fact that from the perspective of a classical simulation algorithm, it seems way too precise or way too difficult to ask it to sample from exactly the distribution D sub C, the outcome distribution of the circuit, so we give it some wiggle room, okay? But this total variation distance metric is not a good proxy for noise. In particular, if you think about what would happen if you say, okay, let's sample from any distribution X that's within a constant total variation distance of the output distribution D sub C. What that means, of course, is asymptotically, as the system size grows, the error or the total variation distance stays the same. That might be reasonable for a classical simulation algorithm, but I'm not an experimentalist, so you can tell me, but I've never seen an experiment that does that, right? You increase the system size and the error doesn't change. Okay. Let me stop briefly for questions. Is that reasonable? Sort of the basics? Yeah. Please, just go. Or wait for the microphone and go.
Just a very simple question.
Yeah.
So the DC, is that like the output of the random circuit, like given a fixed input? The absolute value square wave function?
Yeah, that's right. So in other words, let's be very clear about what D sub C is. So C is a circuit. It's an n-qubit circuit. I pick it randomly, right? Now I start in a fixed input state, so like the all zero state, right? Something really simple. I run my circuit. I measure all n qubits, right? When I do that, I get a distribution over n-bit strings. That's D sub C. So what we're asking the classical simulation algorithm to do is to mimic that behavior, right? Namely, given the circuit C, output a sample from the distribution D sub C. That's the random circuit sampling problem. Any more questions? Is that sort of clear? Yeah.
Yeah, I was just wondering, are you making any assumptions or thinking at all about verifiability of the results? Okay.
That will be very important in the end of the talk, but it's not, for now, no. This is, and it's a great question that you asked. This is one of the sort of the elephants in the room, how to verify these things. But the question that we're asking today is more fundamental than that. It's saying, we can solve this problem in principle, this random circuit sampling problem, but why on earth should it be hard classically, even in an ideal case where there was no noise, you just trusted the experiment, why would that be a hard problem? It's not at all obvious, actually. Right? And that's what we'll talk about today. A separate issue is using, say, cross-entropy to verify the thing. There are connections between the theory I'll describe and the verification. They're not as tight as we'd like. Yeah. Okay. Can I keep going?
Yeah.
Okay. Cool. All right. Now what do we mean by a random circuit? We've already seen this today, but let me say it from my more idealized view. So here's what Google means when they say a random quantum circuit, abstractly. What they want to do is generate a quantum circuit C on n qubits that live on a 2D lattice with around, let's say, square root n layers of Har-random nearest neighbor gates. So each layer might look something like this. The circles here are qubits. The edges are Har-random 2-qubit nearest neighbor gates. This is the first layer, for example. The second layer could look different. It's a 2D lattice, so you could imagine, that the next layer you connect horizontal neighbors rather than vertical neighbors with gates. You start in some easy initial state, right, like all zeros. You apply square root n different layers of this circuit, right, and then you measure all n qubits in the computational basis. What that gives you is a sample from this particular distribution specified by the random quantum circuit, right? Okay, and our goal is to show that solving the same problem is hard for a classical computer. Okay, that sampling from this distribution that's implicitly described by this quantum circuit is something that we can't do with a classical computer. Okay, so how do we do this? Well, it turns out that computer scientists are not very good at understanding directly the hardness of sampling problems. We're very good at understanding, or reasonably good at understanding questions like decision problems. That is, you're given an input and the answer is yes or no. We're reasonably good at understanding search problems. That means you're given an input and the output is some bit string. Maybe there's many bit strings that are correct. We're not so good at understanding this sort of problem. We're sort of changing what we mean by computational problem. It's a sampling problem where the goal is to produce a sample from a particular, complicated distribution that's implicitly specified by a quantum circuit. All right, so what do we do? Well, the first thing we do in all of these, every theory in any quantum supremacy experiment so far, it works the same way. We're going to invoke well-known reductions that were first used in the 80s in actually different contexts by Stockmeyer, which say that if our goal is to prove the hardness of sampling, it suffices to prove that giving a certain additive estimate to the output probability of most random quantum circuits is what's called sharp p-hard. If you know what that means, that's great. If you don't, it means it's very, very hard. Very hard computational problem. Okay? So graphically, we think about it a little bit like this. We think about this reduction as working in the context of a proof by contradiction. We say, let's say for contradiction, there does exist an efficient classical sampler algorithm that samples from this outcome distribution. Well, then there exists, by the Stockmeyer reduction, another algorithm. Now, the algorithm, technically speaking, uses an NP oracle, which means it's not efficient. But the point is, what it does is this algorithm now computes output probabilities. Okay? But there's a star here. There's a complication, which is the sense that we mean compute here is slightly non-standard. We mean, again, giving a certain particular additive estimate to the output probability of most random circuits from the distribution I just described. Now, the goal of this entire talk and the entire theory of quantum supremacy is really to show that this problem, this estimating on average problem, is a hard problem. So such an algorithm should not exist, which then means by the reduction that such an algorithm for sampling should not exist. So it's a proof by contradiction. The entire goal of this talk from now on will be to show that this task is hard, but to see where it fits in, you have to think about this diagram. In other words, we're trying to show it's hard so that if there was a sampler, there would be a too good to be true algorithm for solving this problem, and therefore there can't be a sampler. It's a little bit complicated, but do I have any questions before I move on? We're interested in sampling because, of course, that's what the quantum computer does. The quantum computer doesn't directly compute output probabilities by itself. It samples. Yeah.
You mentioned additive estimator. Do you
Yes.
mean that you estimate the probability to an additive precision of some constant or relative precision?
We mean additive precision. I'll talk about it in a moment.
Okay.
So sorry, in the next slide, I'll say what I mean in a little bit more detail. But let me know if after this you still have a question. Okay, so let's be more formal about what I mean. So what do I mean by output probability? Well, it's what I'm going to call P0 of C. It's just the notation I chose. It's very simple. It's the probability if I start in the all zero state, I apply my circuit, I measure all n qubits, that I get back all zeros. That's P0 of C, just the definition. Now, we're going to consider this what I call the delta random circuit estimation problem. It's the main object of study in this talk. Here it is. We're given, this is a computational problem. It's formalizing this additive estimate on average that I was talking about before. So we're given this input, given this input a quantum circuit C. We want to output an estimate Q to the output probability of C with imprecision delta, that's a parameter of the problem, right? With probability 2/3 over C. Okay? We just told you what the distribution over circuits is. Okay, so this is what I mean by additive error because delta is additive. Yeah? Okay, now, of course, we have to fill in our parameters. So to prove our goal of hardness of sampling, okay, it turns out by the Stockmeyer reduction I just described, it suffices to show that the delta equal 1/2 to the n, where n is number of qubits, problem is sharp p-hard, okay? Why 1/2 to the n? It's very simple. It's because 2 to the n is the relevant dimension of the Hilbert space, okay? So that's our goal. That would suffice to prove hardness of sampling, which then, which is what we want. But we can't do it. And we've been trying to do this for about, since my 2018 paper. And we've gotten a lot better, but we're still not there. So let me explain what we can do. So in 2018, we barely cared about this delta parameter. It wasn't even, it was just, not something we were concerned about. So if we work out what it was like 2 to the minus O of m to the fourth. And I should say m is the circuit size for me. So m is like n times d. So n is qubits, d is its depth. Okay, so we could show that the 2 to the minus O of m to the fourth problem was hard. This was subsequently improved by Ramis Movisag to 2 to the minus O of m cubed in 2019. We then had no progress for a long time, and we were able to recently dramatically improve this to 2 to the minus O of m log m. And Crovey was then able to come up with some subsequent improvements which took the same analysis essentially and made this 2 to the minus O of m, but we're still not where we want, which is 2 to the minus n. Okay. Notice though that for all of this discussion, we can take for most of this discussion, we can take the depth to be constant. So that means that we're only off by a constant factor in the exponent of what we want. Okay. So it's getting a lot closer. It's still not where we want to be. Okay. For boson sampling, we can do something similar. In fact, we can even sort of be very clear about what this constant is. It turns out the goal changes. The delta that you want is 1 over e to the n log n. That's because the relevant Hilbert space changes, and that's the dimension of the Hilbert space. And now we actually can prove hardness in our latest paper of 1 over e to the 6n log n. But there's an annoying factor of 6 remaining between what we want and what we can show. Okay? And toward the end of the talk, I'll actually give you reason to think that maybe this is something that's going to be difficult to bridge. That, you might say, oh, a factor of 6 in the exponent, what's that asymptotically? And we actually think maybe there are some reasons that that's going to be hard to improve. Okay, cool. Okay, let me give a roadmap for the rest of the talk, and then I'll stop to see if anyone has questions. So what are we going to do? I'm first going to go over our 2019 proof of hardness result with, Adam Bolin, Chinmay Nurki, and Umesh Vazirani. To do this, I'm going to give a theoretical result that sort of served as our intuition, and kind of a template for our theorem, which is Lipton's average case hardness for computing the permanent of a random matrix. It's a really beautiful, sort of simple but slick proof. And then I'll show how we adapt Lipton's proof from talking about the permanent of a random matrix, which is some abstract mathematical computation, to talking about the output probabilities of random quantum circuits. Okay, and then we'll show a recent result, which is talking about physical noise. Where we're looking at how robust these hardness results are to things like depolarizing noise and sort of physical noise channels. Okay, so we'll talk about that. Let me stop and ask if there's any questions though before I go on. This is the roadmap. This is where we're going. Yeah. Mm-hmm.
The statement that was in the box. Could you explain what? So Q is supposed to be the output of the circuit, right? So it's a bit string.
Yeah, it's hard to hear.
Yeah. So Q is supposed to be the output of the circuit. So is it a bit string? Is that right? Then I guess
no, it's not right. Q is an estimate to the output probability of the circuit. Right? So, the output probability is just the probability that if I start an all zeros input, I apply the circuit, I measure all n qubits, I get all zeros. That's a real number, presumably, right? That's P0 of C. And now the computational problem I'm talking about is to give an additive estimate to that number.
Okay, I understand. Okay, thank you.
Sorry, just a quick question.
Yeah.
What do you mean with probability 2/3 over C?
That's right. So this is why we're talking about random circuits, right? Because implicitly in the background, what we have is a distribution over circuits. I just specified what that distribution is, right? That comes from, fixing the sort of architecture, choosing the gates randomly, and so on, right? Making some number of layers, okay? And so that's the distribution I have in mind. And then the point is that what I want to show is hard is this problem in the blue box, which amounts to giving a good additive estimate. Let's call it a delta additive estimate to this output probability for most of the circuits drawn from this distribution. But with probability 1/3, let's say, right, I can output nonsense and still solve the problem. That's what that means, right? 2/3 of course, arbitrary number. It's something that's greater than a half would be fine. Yeah, yeah.
You mentioned that constant depth is, sorry, you mentioned that constant depth is fine, and Google has square root of n, so.
That's right. It sort of depends on a whole bunch of different things. I think unless you really care about getting the right precision, it's easier to think about square root n. It will make all of what I've discussed a lot easier. But there are subsequent papers that we've written where we're able to adapt most of these arguments to the constant depth case. It's not at all obvious though. Like we had to write a paper on it, and the distribution turns out to be different. It's no longer Haar random gates. It's a little bit messy. But yes, in principle, when you're thinking about this precision, it's fair to think about the depth as a constant because we've worked things out in that case.
But is depth, let's say, 4 fine, or we need still have?
Yeah, sufficient. Let's say a sufficiently large constant.
Okay.
Yeah. Mm-hmm. More questions? We're good? Okay. All right, great. Okay, so let me now describe one of my favorite mathematical proofs. I think it's very clever, and it's also very simple. This is Lipton's proof in the early 90s that the permanent is what's called average case hard. In other words, this is saying that not only is the permanent of a matrix a hard problem in the worst case, which means that we shouldn't expect an algorithm to compute the permanent of an arbitrary matrix over, say, a finite field, but even computing most random matrices, okay, is a hard problem. That's actually extremely special. It's something that we don't actually have a good handle on for most problems, but the permanent has this property. So the first thing is, like I said, the permanent has been known since the 70s to be worst case hard to compute. This is very surprising, right? Because intuitively, at least, it seems like the permanent looks a lot like the determinant, and yet somehow there's this huge discrepancy and difficulty between the determinant, which is easy to compute using Gaussian elimination, and the permanent, which is like harder than NP hard. It's like super hard. We still don't understand exactly why this is true. It's one of the biggest problems in theoretical computer science. Okay, but our interest now is to boost this hardness from worst case hardness, which is the hardness of computing an arbitrary matrix, to average case hardness, the hardness of computing most random matrices. Okay, and to do that, we'll use a simple algebraic property of the permanent, which is that it's a degree n polynomial in the n squared variables. The n squared variables here are the n by n matrix entries, right? Because n times n is n squared. All right, now how are we going to do this? Well, first let me give you the formal setting that I'm thinking about. This is always what we talk about when we say, average case hardness or worst to average case reduction. The goal is to compute the permanent of X for your favorite worst case matrix X. You give me this matrix, it's completely arbitrary, you want me to compute it. But I don't have this ability, right? The only thing I have at my disposal is a faulty or average case algorithm O that does the following thing, right? So O does this, it's given as input a matrix Y, again with entries over a sufficiently large finite field, and then it outputs the permanent of that matrix Y with high probability over Y. Okay? So again, there's some matrices for which this faulty algorithm, well, it's faulty, it gives you the wrong output, something that's completely uncorrelated with the permanent. The only thing, and you don't know when it gets it right or wrong, the only thing you know from the end user of the box O is that it gets it right most of the time. Okay? And now the question is, how do we use this box O, this faulty box, to correctly compute the permanent of our worst case matrix X? Okay? So the claim is that you can do this. And it's actually quite clever and simple. It's a polynomial extrapolation argument. Let me explain how it works. So here's the idea. Let's choose n+1 fixed non-zero points in our field FP. We'll call them T1, T2 through Tn+1. All right? That's why we need a sufficiently large field to have n+1 points. Okay? Now, we'll pick a uniformly random matrix. I'll call that R in our field. And we'll consider the line A of T, which is equal to X. That's our worst case matrix. That's the matrix we want to know the permanent of, but don't. Plus T times R. Okay? So just plus a random shift. Okay? Now, two observations. They're super simple, and we'll specify how the proof should work. So first is what I call the scrambling property, which is that for each I individually, A of T sub I is a uniformly random matrix over our field. That's not hard to see. That's because we took worst case matrix X, we shifted it by something random. What you get out is something random, something uniformly random. Okay? So for each I individually, A of T sub I is a uniformly random matrix. Observation 2. There's a univariate polynomial property here, sort of lurking here, which is that the permanent of A of T is a degree n polynomial in the single variable t, right? That's also not hard to see. That's inherited, of course, from the algebraic property of the permanent itself, that the permanent is itself a degree n polynomial in n squared variables. Now the permanent of a of t is a degree n polynomial in one variable, in t. Okay? But now we sort of spelled out how the proof should work. So here's what we do, right? We use our box, O, and we evaluate it at A of T1, at A of T2, at A of T3, and so on, right? N plus 1 times. Now, by the fundamental theorem of algebra, right, these N plus 1 points uniquely define the polynomial A of, permanent of A of T, right? The reason for that is, of course, we've specified single variable real polynomial on N plus 1 points, it's degree N, okay? So now we can use sort of grade school polynomial extrapolation, given these points, right, to reconstruct the polynomial permanent of A of T. Once we do that, it's trivial to get back the permanent of X. How do we do that? We simply evaluate it at T equals 0, because when T equals 0, we have the permanent of X. The reason this works, right, is because the probability of success of this algorithm is sufficiently high. It's like 1 minus 1 over, say, n plus 1, something like that, so that with probability 2/3, right, all of the n plus 1 points are going to be correct, okay, by a union bound. That's why this works. Okay, sorry, let me take it. This is a little bit of a subtle proof if you haven't seen it before. Any questions about this, how this works? Yeah.
Just a quick question. I don't see how you're using uniformity and randomness here at all. It seems like you just argued that any plus 1 things are hard.
Right. No, you are only in one sense. It's a great question. There's not a huge dependence on the distribution here. But you are using it in one sense, which is that this algorithm, it only, by definition, by assumption, it works with high probability relative to the uniform distribution over the matrices. So that's how I'm using it. But of course I could change the distribution that it works over, and then you could ask if you can extend this sort of argument. In many cases you can't.
But I can't choose a bunch of very easy pieces and try to interpolate.
No. Right. Exactly. That's sort of what's keeping you from doing that. That's a great question though. Any others? Okay, great. So let me move on. So now what I want to do is try to adopt this Lipton's argument from the permanent of a random matrix to the output probability of a random circuit. And here's how it's going to work. So it turns out there's an algebraic property hiding here too. Much like the permanent, the output probability of a random quantum circuit has polynomial structure. To see this, we can consider a circuit C, break it apart into its 2-qubit gates. So these are all, I'm just assuming it's 2-qubit gates. It's not that important. Cm minus 1 through C1, so 2-qubit gate. And the polynomial structure simply comes from the path integral, which allows us to write the output amplitude of, this quantity here as this enormous sum over paths. There's an exponential number of paths, but the point is the value of each path is quite manageable. It's just the product of m gate entries of the circuit, right? That's what these are, right? Okay. And so it's a polynomial of degree m in the gate entries. And so by the Born rule, we simply square the output probability. We take the norm and square it. It's not hard to see that P0 of C, the output probability, is simply going to be a polynomial of degree 2m. Okay? So let's try to use this structure to adapt Lipton's proof. Here's what we're going to do. It's not going to quite work, but it will almost work. We'll fix m. M, remember, is the size of the circuit. That's the number of gates in our worst case circuit, which is C. So the circuit we want to know the output probability of. We'll fix m Har random 2-qubit gates. We'll call those H1, H2 through Hm. Now, the main idea is that, again, what do we want to do in Lipton's proof? What we want to do is we're assuming the ability to compute the output probability of a random circuit, right? But I give you a fixed circuit, C, and I ask you to do it. Well, you want to make that look more random so that you can use your ability to compute the output probability of your random circuit to compute the output probability of C. So we want to scramble our circuit. How are we going to do this? Well, we're going to take each gate in our worst case circuit C, that's Ci, multiply it by Hi, right? Well, if we do that, we've just completely scrambled the circuit by the invariance property of the Har measure. Right? It went from a fixed circuit to a totally random circuit. So we're not going to stop there, though. We're going to now multiply by e to the minus I little hi theta, where we'll think of hi as the log of these Har random matrices. Okay? Now, why do I like this? Well, I claim it has a sort of a Lipton-like property. Namely, if I think about theta as a sufficiently small parameter, right, then each gate is really close to Haar random. Because I did very little by multiplying by e to the minus I little hi theta, right? But what happens if theta is not small? What happens if theta is 1? Well, if theta is 1, then we get back our worst case circuit. Why is that? Because what we've implemented is Ci times hi inverse. Okay, well the hi, cancels with hi inverse and we get back our worst case circuit. Right, so we might hope to have sort of a high level strategy now that's very similar to that of Lipton. In other words, we might take several non-zero but small thetas, right? For each one we have a corresponding sort of correlated but individually looks random circuit, which I'll call C prime theta 1, C prime theta 2, and so on, right? Then I compute the output probability of each of these random looking circuits because I have that ability by assumption, right? Then I use polynomial extrapolation to compute the output probability of my worst case circuit. Right? That's the strategy. It doesn't quite work though. The reason is very simple. It's because we don't quite have a polynomial here. It's for a simple reason, which is that e to the minus I little hi theta is not a polynomial. It's not a fixed degree polynomial in theta. It's just not. So what do? We do what any physicist would do. We consider taking a fixed order Taylor series truncation of e to the minus I little hi theta. Well, now it has what we want, right? In other words, the final way of scrambling the fixed circuit C is Ci times hi times the fixed kth order Taylor series truncation of this e to the minus I hi theta. All right, so now each gate entry is a polynomial in theta. All right, why is that? Well, that's because the Taylor series is a polynomial in theta, right? And then by the path integral, so is the output probability of the circuit. Okay? So then we can extrapolate, and at the end of the day, once we've reconstructed this polynomial, we can evaluate it at 1. When theta is equal to 1, that gives you back the output probability for your worst case quantum circuit, which is your hard problem. Okay, great. Questions about this before I go on? Great, yeah, that's a great question. So you have to, of course, take into account the truncation error. It's actually quite subtle. This is the first thing I'm going to talk about the next thing. If you think about what you're doing when you're truncating, right, you're actually now arguing about the hardness of a distribution of circuits that's supported over circuits that are sort of slightly non-unitary, right? And so in fact, this is more of the starting point of our 29 paper than the ending point. What I see as our main technical result in the paper is we sort of said the following. This is our what I consider our main technical theorem. We said, at the beginning, remember, we didn't care about exactly computing the output probability. We really cared about an estimate. Remember this 1 over 2 to the n estimate? And so what we formally proved is that with respect to such an estimation, which is what we cared about to show hardness of sampling in the first place, actually it doesn't matter if you talk about this truncated circuit or the unitary circuit. And we formally proved that. In other words, we showed that estimating the output probability of this truncated random quantum circuit with, is hard if and only if estimating the output probability of the unitary circuit is. And that's a technical proof. It takes a lot of work, but intuitively, I think it's pretty clear why this is true. It's because the truncation error that we're making, it's some arbitrary kth order. You can take k to be some polynomially large parameter in the input size, is so much smaller than the desired precision. Right? So if we're somehow going to, say that this is a hard problem for some very large precision, right? Then it shouldn't really matter that we're like truncating the Taylor series, which is a much smaller error. Well, anyway, that's the intuition. You can read the proof. Okay, since then, though, this was only a figment of the analysis. It didn't change the experiment, to be clear. Nothing changed. But in recent work, Ramis Mobasag has given related arguments, still a sort of Lipton-style reduction, but a more elegant path that stays unitary throughout the entire path between the random circuit and the worst-case circuit. And so it sort of takes our work, but then eliminates the need for truncations altogether, which was nice. It made the analysis far simpler. Okay? And then more recently, we've been able to extend the imprecision of this result to additive error 2 to the minus O of m. Okay? I already discussed that. Okay, so now Okay, great. So far we've talked about imprecision, sort of like an additive error to the estimate of an output probability, but not physical noise. Right? Nothing here was talking about some noise channel that might occur in physics. And so that's important, of course, because we know with a near-term quantum system, without error correction, noise completely overwhelms. Right? I mean, for example, in Google's RCS experiment, they estimated something like 0.2% fidelity, 99.8% noise, and of course, with every expectation that if they had made their system larger, the signal would exponentially decay. That's what you'd expect if you're not correcting your errors and you're not improving your noise rate, right? And so how do we understand this theoretically? Well, one way to do this that we thought about quite a bit is to sort of fix a reasonable noise model. So it turns out the argument I'm about to describe is not so sensitive to the noise model, but here's a natural one, right? You could imagine that each ideal random gate, Ci, is followed by the 2-qubit depolarizing noise, right? So this is kind of the simplest thing I would think of. And so this is a depolarizing noise channel, of course, where I think of gamma as a sufficiently small constant, okay? That is, one way of thinking about this is but you can think about choosing a noisy random circuit by first picking an ideal circuit, C, from the random circuit distribution, just like we did before, and then the environment, or something that's not up to us, right, gets to pick these noise channels. Okay, these noise operators, rather, right? So, for example, in the case of depolarizing noise, we think of this distribution that I'm calling script n as over sort of random 2-qubit poly operators. Okay, and then at the end of the day, when we measure all n qubits, we get a sample from the output probability of what I'm calling n.c. It's just a abusive notation. I simply mean we're multiplying the noise operators, the poly operators, by the gate by each gate, right? Without ever learning what the noise operators were. Okay, that's the model. And actually, the point from here is super simple. It's that it's not hard to see at all that similar hardness arguments work with noise. Similar hardness arguments to the ones I just described. So why is that? Well, it's because the output probability of this noisy circuit can still be written as a weighted sum of path integrals, right? Here's what I mean by that. Well, you can write the output probability of the noisy distribution as this expectation value over the noise operators, right? Because we're averaging because we don't know what they are. And the point is, this can be written in this form. I'm just writing out what that expectation is, the sum of a whole bunch of probabilities of seeing each noise operator times the output probability of the noisy circuit. And the point is super simple. It's that this is still a polynomial of degree 2m in the ideal gate entry. So we sort of changed the sum a little bit. We added more terms, but the original property that we were using for hardness didn't change at all. Okay? Okay, great. So using essentially the same arguments as before, what we realize is the following theorem. Providing the noise rate gamma is sufficiently small constant, and that's important. There's a transition there. It's related to the error detection threshold of the architecture, actually. But providing it's sufficiently small, we can prove it's hard to compute this noisy output probability to exactly the same imprecision as before. That's 2 to the minus O of m, where m is the number of gates in the circuit. Okay? So that's our noisy hardness result. But why do we care about this? Well, we care about this for an interesting reason. There's also a trivial classical algorithm in the noisy case. Well, what is that? Well, there's a phenomenon that's going on here. It's super intuitive. If you have uncorrected depolarizing noise and you keep applying many layers of your circuit and you don't do anything about it, you keep going and going and going, eventually you're going to converge to the uniform distribution. You're adding entropy to the system. If you're never correcting it, you're converging to the uniform distribution. And it's clearly not hard to output a probability from the uniform distribution. Even I can do that. The answer is 1 over 2 to the n, independent of the circuit, right? So the key question here that's, I think, very interesting, we've been thinking about this a lot, is how accurate is this trivial algorithm? In other words, from my perspective, what is the formal imprecision of this trivial algorithm that estimates the output probability of the noisy circuit by simply outputting 1 over 2 to the n? How well does that work? Well, there was a conjecture, which was made in the context of the quantum supremacy paper, actually a little bit before it, which is that for sufficiently deep circuits, which was not really quantified explicitly, the imprecision of this trivial algorithm, or equivalently the closeness to the uniform distribution, or the maximally mixed state of this noisy circuit, was scaled like 2 to the minus O of gamma, that's the noise rate, times D times N. Okay? So in other words, it's exponential not only in the circuit depth, but in the number of qubits. Okay? Now, we've been thinking a lot about this conjecture because it's actually quite daring. It's sort of saying if you keep your depth, right, fixed, you don't change it, but you make your qubit act on more qubits, your circuit act on more qubits, you're getting closer to the uniform distribution exponentially. Sort of bad news if you think about that for near-term algorithms, if that was really the case. And we think there's sort of a mixed message. We can prove that this is true in some very sort of contrived toy models of deep random circuits. But recent work, which was in QIP of this year, or of last year, I guess, shows that we actually can prove that it's not true for shallow circuits. So when the depth is sufficiently shallow, when it's like log depth or less, can actually prove that, that you don't have this explicit dependence of n in the exponent, right? That you only have a dependence of d. But we don't know if that's true for deeper circuits. Okay, but let's assume Google's conjecture is true for the moment, that there's some parameter regime in which we can get this, 2 to the minus O of gamma times d times n convergence to uniformity. Well, then what have we done? Well, there's something really interesting here. It's very simple to see. Well, on the one hand, we have a hardness result. Right? We have a hardness result that says for noisy circuits, it's hard to compute the output probability to imprecision 2 to the minus O of m. Right? We can prove that. But on the other hand, we have an easiness result. And that easiness result works for essentially the same imprecision, 2 to the minus O of m. Okay, now to be clear, like the constant in the exponent is clearly different. Right? You can't have an easiness and a hardness result with the same imprecision. But the point is, this is becoming tight. If you assume Google's conjecture, then we have hardness, at 2 to the minus O of m, some O of m, and easiness at a different 2 to the minus O of m, for a different constant in the exponent. Okay? So it's really sort of a tight characterization of hardness for noisy circuits. But what's the upshot for the noiseless case? Right? Let's think about the noiseless case, where we were not thinking about depolarizing noise, and there was no obvious algorithm which was converging to uniform distribution, so outputting 1 over 2 to the n. Well, it's sort of interesting. What we're saying is the following. If we want to dramatically improve the robustness of the noiseless case, right, then we're going to have to invent new proof techniques that are not robust to noise. Why is that? Because we know that the noisy case is essentially tight. We can't improve those results. We also know that I did very little, if you didn't notice, to adapt the techniques from the noisy from the noiseless case to the noisy case. So unless we come up with techniques that will not work to improve the robustness in the noisy case, we can't hope to improve the noiseless case, because the noisy case is essentially tight. Okay, let me, I might have like one minute remaining or something. Okay, let me just give some future directions, because my group works on random circuits essentially for a living now, so we have a whole bunch of different things. Two sort of elephants in the room. The first one, is there any useful reason that we should be implementing random quantum circuits, or is it just a proof of principle or some benchmark? Well, we're thinking about this. We've thought a lot about a proposal by Aronson which shows how to implement certified randomness using random circuit sampling experiments. We have a lot of sort of theoretical results which sort of back a conjecture made by Aronson in the context of his proposal. Okay, so you can read about that on the archive. Two, benchmarking or verification. This is the second elephant in the room, right? So far we've just talked about the hardness in principle of sampling from this hard distribution, but how do we, if we don't trust the experiment, how can we check that it's really doing what we think it's doing, right? Okay, I'm going to leave that to this archive paper, which talks a lot about that from my group recently. And then finally, I already mentioned it, how close are our output distributions of noisy quantum circuits to the uniform distribution? I have a new paper all about this question. Okay? Thanks a lot.
Okay, well, even though time's up, I think we can take a few minutes for questions.
Thank you. I think about these circuits in a different way than your mathematical proofs, in the sense that if you have a circuit and you have a bit flip or phase flip, then the output speckle distribution completely changes and it's uncorrelated. Is there an easy way to see that, and how does that like relate to your proof? Because that seems to be like an interesting way to think about it.
Okay, first of all, I agree with you. I think there's some intuition to be had there. And I don't know how to connect the intuition to this formal proof. That's the real answer to your question. I think, though, that you have to be a little careful. So we've thought a lot about what I think most directly characterizes this speckle pattern sort of hardness, which is the cross-entropy benchmark. And that the cross-entropy benchmark is sort of characterizing the heavy outcomes, which corresponds to the constructive interference, right? We have not been able to formalize why, scoring sufficiently well on that benchmark is hard. So this is the best thing that we can do at the moment, where we have a very, very formal proof of something that as of yet is not directly verifiable, right? So you would need to use our theory results, and then on top of that would use something like cross-entropy to verify that the experiment was implementing anything close to the correct thing. I think it's actually a really great question, in fact. I don't have a good formal reason to think that this hardness proof that I just gave you should match up so much with this sort of, intuition.
Okay.
Yeah.
Thank you.
Great talk. Thanks a lot. So you mentioned that when for the proof for the hardness of this noisy computation, the gamma has to be small to avoid the transition behavior.
That's a great question. It's the error detection threshold for whatever architecture you choose. So if you have like a 2D circuit architecture, it's that. I've got to be honest with you, as a theorist, we didn't even calculate that.
I see.
So I can't tell you a real number. I expect it's not such a great, it's a pretty small, but we didn't do that.
I see. So this gamma is just a constant, but it is a constant. Independent of system size. Anything.
Precisely. Yeah.
I see.
Okay, one last question. We're in the back. I'll run it back there. And maybe Ehud, you want to start setting up? I don't know where you are.
Hi, Bill Mano here. Nice talk. I'm still confused about the 1 over 2 to the n if you have a fixed circuit depth. Would you even expect the variation over the piece over circuits to be that small then? I mean, I guess you only get to 2 to the n when you're really deep, no?
That's actually a really great question, and the honest answer is we don't know. It's something we've thought about. Let me explain it in my language, okay?
For sure, it's not, no? I mean,
it's not quite known. So here's what's sort of interesting. For sufficiently deep circuits, right? We understand the statistics of random circuits pretty well. They're what's called Porter-Thomas, right? Yeah. And Porter-Thomas sort of formalizes to us why a 1 over 2 to the n output probability is non-trivial.
Right.
Right? Now, when you have a sufficient, because it's not, most of the time it's not like 1 over 2 to the n, just outputting 0 doesn't work very well, right? But when you have a sufficiently shallow depth circuit, say depth 4 or 5, it's not clear at all that you've converged sufficiently well to Porter-Thomas so that this would give you a meaningful estimate. In fact, in some cases you can show it's not the case. It depends on the distribution and so on. So I would say that, despite what you might have thought about in my talk, I'm not comfortable categorically conjecturing hardness of a depth 4 quantum circuit for any distribution that you give me. Right. But I do believe that you can cook up distributions that are probably hard.
Yeah, let's chat a bit longer. I think it's not 1 over 2 to the n for any fixed test. That's just not true.
Sorry, say it again. Yeah, and then you wouldn't get hardness, right? Yeah. Another thing I'll say is that, our result just showed that the worst case the average case is as hard as the worst case. It could be that the worst case is easy, right? It just so happens when you have a sufficiently deep circuit, you have worst case hardness, and then you can use our reduction to show that the average case is as hard as the worst case. Okay.
Okay, let's thank Bill once again.